So we have a physics Ph.D. qualifying exam, practice problem number 7 in classical mechanics. So a particle moves under the potential V of x equals Fx, where F is constant. For part A, write the Hamilton-Jacobi equation. For part B, find the complete integral S of x t semicolon alpha. Obtain the particle trajectory from the Hamilton-Jacobi solution for part C. For part D, verify that the result agrees with Newton's second law. And for part E, discuss the advantages of Hamilton-Jacobi's theory for integrable systems. Okay, so this is a Hamilton-Jacobi theory problem. Part A. Okay, for a one-dimensional particle with V of x equals Fx, the Hamiltonian is h equals p squared over 2m plus fx. The Hamilton-Jacobi equation is this partial derivative ds dt plus h of this x, comma, partial derivative here ds dx, comma t equals 0. Since p equals this partial derivative here ds dx, then we could say that partial derivative ds dt plus 1 over 2m times this partial derivative ds dx quantity squared plus fx equals 0. So that is part A. For part B, find the complete integral here. Okay, because h has no explicit time dependence, we try this s of x comma t semicolon alpha equals w of x semicolon alpha minus alpha t, where alpha is the conserved energy. Substitute into the Hamilton-Jacobi equation negative alpha plus 1 over 2m times this quantity dw dx squared plus fx equals 0. This derivative here dw dx quantity squared equals 2m times the quantity alpha minus fx. So dw dx equals the square root of 2m times the quantity alpha minus fx. Now we go about and integrate that, and w of that x semicolon alpha equals negative 2 times the square root of 2m over 3f times this quantity alpha minus f of it, alpha minus fx raised to the 3/2. So s of xt semicolon alpha is equal to negative 2 times the square root of 2m over 3f times the quantity alpha minus fx to the 3/2 power minus alpha t. And as a note, s of xt equals w of x minus et, and that's because the Hamiltonian is time independent. So that's part B. Moving along now to part C. For part C, obtain the particle trajectory from the Hamilton-Jacobi solution. Okay, so for part C here. Let me just take this down. Sorry about that. Okay, so for part C, Hamilton-Jacobi theory says this partial derivative ds d alpha equals beta, where beta is another constant. So this partial derivative ds d alpha equals negative square root of 2m over f times this quantity alpha minus fx to the 1/2 minus t. Beta equals negative t minus square root of 2m over f times square root of alpha minus fx. And now alpha minus square root of alpha minus fx equals negative f over the square root of 2m times the quantity t plus beta. Alpha minus fx equals f squared over 2m times t plus quantity t plus beta squared. So we're going to get for x of t equals alpha over f minus f over 2m times the quantity t plus beta squared. Okay? So we could say this is the trajectory, and it is a parabola in time as expected for a constant force. And equivalently, using initial conditions, x of t equals x naught plus v naught t minus f over 2m t squared. And a note here, in Hamilton-Jacobi theory, the generating function s defines a canonical transformation to new coordinates q comma p, where p equals alpha is constant and q equals this partial derivative ds dp. So partial derivative ds d alpha equals beta, where beta is another constant. So that's letter C. And for letter D, they want us to verify that the result agrees with Newton's second law. Okay, so for part D, since v of x equals fx, the force is F sub phys equals negative dv dx equals negative F. Newton's second law gives us mx double dot equals negative F. So x double dot equals negative F over m. From the trajectory, x of t equals x naught plus v naught t minus f over 2m t squared. X naught equals v naught minus f over mt, and x double dot equals negative f over m. So the Hamilton-Jacobi result agrees with Newton's second law. And for the last part of the problem, letter E, we want to discuss the advantages of Hamilton-Jacobi theory for integrable systems. So here, the Hamilton-Jacobi theory is useful because it reduces the problems to partial differential equations, identifies constants of motion, gives trajectories directly, leads to canonical transformations, it translates to integrable systems, and is connected to quantum mechanics. And for completely integrable systems with n degrees of freedom, it allows transformation to action angle variables, reducing the dynamics to trivial linear evolution. Okay, so that's all for this problem. Thank you very much and have a great day.